In this presentation, I'll go through some notes from Chapter 10 of book, Designing Data-Intensive Applications. Chapter 10 is called Batch Processing. In this chapter, we explored the topic of batch processing. We started by looking at Unix tools such as awk, grep, and sort, and we saw how the design philosophy of those tools is carried forward into MapReduce and more recent data flow engines. Some of those design principles are that inputs are immutable, outputs are intended to become the input to another as yet unknown program, and complex problems are solved by composing small tools that do one thing well. In the Unix world, the uniform interface that allows one program to be composed with another is files and pipes. In MapReduce, that interface is a distributed file system. We saw that data flow engines add their own pipe-like data transport mechanisms to avoid materializing intermediate state to the distributed file system, but the initial input and final output of a job is usually SDFS. The two main problems that distributed batch processing frameworks need to solve are, first, partitioning. In MapReduce, mappers are partitioned according to the input file blocks. The output of mappers is repartitioned, sorted, and merged into a configurable number of reducer partitions. The purpose of this process is to bring all the related data, example, all the records with the same key together in the same place. Post-MapReduce data flow engines try to avoid sorting unless it is required, but they otherwise take a broadly similar approach to partitioning. The second is fault tolerance. MapReduce frequently writes to disk, which makes it easier to recover from an individual failed task without restarting the entire job, but slows down execution in the failure-free case. Data flow engines perform less materialization of intermediate state and keep more in memory, which means that they need to recompute more data if a node fails. Deterministic operators reduce the amount of data that needs to be recomputed. This chapter discusses several join algorithms for MapReduce, most of which are also internally used in massive parallel processing databases and data flow engines. They also provide a good illustration of how partition algorithms work. So some of those join algorithms are sort-merge joins. Each of the input being joined goes through a mapper which extracts the join key. By partitioning, sorting, and merging, all the records with the same key end up going to the same call of reducer. This function can then output the join records. Second is broadcast hash joins. One of the two joins inputs is small, so it is not partitioned, and it can be entirely loaded into a hash table. Thus, you can start a mapper for each partition of the join input, load the hash table for the small input into each mapper, and then scan over the large input one record at a time, querying the hash table for each record. Partition hash joins. If the two join inputs are partitioned in the same way, that is using the same key, same hash function, and same number of partitions, then the hash table approach can be used independently for each partition. Distributed batch processing engines have deliberately restricted programming models. Callback functions are assumed to be stateless and to have no externally visible side effects besides the designated output. This restriction allows the framework to hide some of the hard distributed systems problem behind its abstraction. In the face of crashes and network issues, tasks can be retried safely, and the output from any failed task is discarded. If several tasks for a partition succeed, only one of them actually makes its output visible. Thanks to the framework, your code in a batch processing job does not need to worry about implementing fault-tolerant mechanisms. The framework can guarantee that the final output of a job is the same as if no faults had occurred, even though in reality, various tasks perhaps had to be retried. These reliable semantics are much stronger than what you usually have in online services that handle user requests and that write to databases as a side effect of processing a request. The distinguishing feature of a batch processing job is that it reads some input data and produces some output data without modifying the input. In other words, the output is derived from the input. Crucially, the input data is bounded. It has a known fixed size. For example, it consists of a set of log files at some point in time or a snapshot of database contents. Because it is bounded, a job knows when it has finished reading the entire input, so job eventually completes when it is done. Here are some of the highlights of this chapter. The first highlight is the Unix philosophy. So here are some of the Unix philosophies that are referenced in the chapter. Make each program do one thing well. To do a new job, build afresh rather than complicate old programs by adding new features. Expect the output of every program to become the input to another, as yet unknown program. Don't clutter output with extraneous information. Avoid stringently columnar or binary input formats. Don't insist on interactive input. Design and build software, even operating systems, to be tried early, ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild them. Use tools in preference to unskilled help to lighten a programming task. Even if you have to detour to build tools and expect to throw some of them out after you have finished using them. Philosophy of batch process outputs. If you introduce a bug into code and the output is wrong or corrupted, you can simply roll back to a previous version of the code and rerun the job, and the output will be correct again. Or even simpler, you can keep the old output in a different directory and simply switch back to it. Databases with read-write transactions do not have this property. If you deploy buggy code that writes bad data to database, then rolling back the code will do nothing to fix the data in database. As a consequence of this ease of rolling back, feature development can proceed more quickly than in an environment where mistakes could mean irreversible damage. This principle of minimizing irreversibility is beneficial for agile software development. If a map or reduce tasks fails, the MapReduce framework automatically reschedules it and runs it again on the same input. If the failure is due to a bug in the code, it will keep crashing and eventually cause the job to fail after a few attempts. But if failure is due to transient issue, the fault is tolerated. This automatic retry is only safe because inputs are immutable and outputs from failed tasks are discarded by the MapReduce framework. The same set of files can be used as input for various different jobs, including monitoring jobs that calculate metrics and evaluate whether a job's output has the expected characteristics. For Unix tools, MapReduce jobs separate logic from wiring, that is configuring the input and output directories, which provides a separation of concerns and enables potential reuse of code. One team can focus on implementing a job that does one thing well, while other teams can decide whether and when to run the job. This concludes Chapter 10 Batch Processing Notes. Hope this was useful. Have a nice time. Like and subscribe for more such content.